Okay, so again, it's worth reiterating that, yeah, Josh, I'll talk to you after class about that. I think you sent me something at 3. We'll talk. We'll figure something out. So don't leave the Zoom until you and I talk. The way you want to think about this, a very simple way to proceed is to think about this backwards E is just a shorthand for there exist. That's the best, simplest way as a beginner you can think. So again, if you're thinking, I'm afraid of these symbols, all you want to do right now is say, okay, what do humans realize is instead of having the right there exist over and over again, we're going to create a new symbol, this backwards E. So I want to know, am I lying to you when I say this English sentence? Yes or no? That's exactly what we're asking. Is it true? Is it false? And so what you need to understand is, for this to be true, we only need to find one example where it's true. To be true, we need to only find one example. So what you have to ask yourself, is there a number who, when you cube it, it spits out -1? And the answer is yes. One way to see it is to just solve. What would x be? Take the cube root of both sides. Oh, the cube root of -1 does exist. It's -1. So note, x equals -1 works. Does anybody not see that? It works. If I take -1 and cube it, that's -1 times -1 times -1. The rules of multiplication tell me that is -1, and so that is true. All I needed was to find 1. Now, it turns out it's the only number that satisfies this, but we found it, right? So it's a true statement. Does anybody have a question about this piece? Now, let's look at one. Let's look at, say, one like C. So for C, we'll use what's called the universal quantifier. C reads this: for all x, x squared is not equal to x. So this reads, oops, excuse me. For every real number x, x squared is not equal to x. That's how that reads. And so is this true or false? So to be true, this must hold for every x. Well, that's clearly not the case, because I can think of a number right away that it's not true. If I take the number 1 and I square it, I get 1. It does not meet this criteria. So, since 1 squared equals 1, 1 is enough evidence to conclude the statement is false. So, look, there's no doubt that this stuff is confusing. There's a lot happening here. We're asking you to sort of learn a new language, and it's sort of in symbols, and it's also in learning this new language, we're asking you to remember some basic facts about numbers. And again, it gets very confusing. As soon as you think you understand one of them, then you're like, oh my God, what's the other quantifier? And then it just kind of blows up. I mean, you and I talked about that when we talked last week. So, you got to keep that in mind. Does anybody have a question about C? Okay. Okay, so let's look now at some of the ones that become a little more involved. So, I mean, Michelle, I think you asked about F, G, and H. Okay. So now what makes F, G, and H a little more difficult is now we have two variables or two things that we're interested in. So let's look at F. So if we look at F, this says for all real numbers X, for all real numbers Y, and when we add them together, we get 3. So let's think about how we would read this. Do we read this for all real numbers X and all real numbers Y? How do we read this? This is an important thing for you to understand. We need to have a convention. How would we read it? Right? That we all agree on. Sort of like we all agree that we're going to read left to right. So I think, you know, this goes back to a couple classes ago. Mackenzie, you asked a question and we talked about how do you interpret some of these things. Okay, so let's just say we translate it directly. This reads, for all, that's silly. For every real X, for every real Y, X plus Y equals 3. Now, is it true? The one way you could think about this is say, okay, let's just take two real numbers. When I add them together, does it equal 3? And clearly the answer is not always the case, right? This is not true for every X and for every Y. I mean, it's absolutely ridiculous to think that. I mean, take two numbers, 0 and 0. Do you add them together to get 3? No. And so since we're saying it has to be true for every X and for every Y, then this has to be false, because we could think of lots of places where this doesn't hold. Is that clear? Are you guys at home, is that clear?
So it's false because you can have a
false, yeah, because we're lying to you. I lied to you. If you read that English sentence, forget about the symbols. If I read that English sentence, am I telling you a truth or am I telling you a falsehood?
false.
False, right? I mean, does that make sense, Mackenzie?
Yeah, it does. I was just clarifying.
And it's easy. So when I say does it make sense, I'm not asking you guys to be experts at this. Does that make sense?
Yes.
So you could think of this as for every real X and for every real Y, or you can read it the way I've written it. Does that make sense? All right, now let's go. I keep losing. Let's go to G. Now, we often see in mathematics, it's very common to see quantifiers doubled like G and H, where you have for all X, there exists a Y. This is a very common thing. And you can think of it as a game. You know, Fink gives me an X, any X he wants. I have to go find a Y. I have to find it because the claim is that it exists somewhere. So how do I determine it? So we talked about this briefly last class. And so let's look at one like G. Now let's change color. This green is making me mad. It's making me think of money, and I don't have enough of it. So I want more. Uh-oh. The computer now said, yeah. What? Malfunctioning, my friends. So now we have this beautiful statement. For all X, there exists Y. such that x equals y squared. So I think this is the problem we actually did last week. I'm not, maybe it is, maybe it isn't. So either way, we're going to do it again. How should you read this? How would we read this? Well, this reads for every x, or for all real x, there, oh my God, I did it again. There exists y such that x equals y squared. So once again, we want to ask ourselves, if I read this sentence out loud and I say it to you, am I telling you a truth or am I telling you a lie? So let's play the game, and I'm going to pick on Fink just because he's right here and he's been in class with me before. Fink, hello. Fink, pick any number you want. I don't give a damn what it is. 5. Fink picks 5. Is there some number out there that is equal to, or excuse me, let me rephrase that. Is there some number out there that I can square to get 5? Yes or no? Yeah, what is it? Don't overthink it. What the hell is it? What number squared equals 5? Give you a hint. It has 5 in its name. What? Just say it. The square root, right? Just don't overthink this. Yes, that's it. Right. Okay, now pick any other real number. 9. What number satisfies that 9 is equal to y squared? Y would be square root of 9. Okay. What if you pick negative 16? Does that have a partner in the real numbers? Don't get cute and start spitting something else. No, it doesn't. There's no number out there that you could square that gives you negative 16. So although it's true for all positive numbers and it's true for 0, it ain't true for negative numbers. Does that make sense? We didn't just find one counterexample. We found infinitely many. So this statement, this is true if x is greater than or equal to 0. Just set y equal to the square root of x. It's false for x less than 0. And so the conclusion that we make then is the following. Therefore, this statement must be false. Because I'm lying to you. If I tell you this works for all real numbers, I'm lying to you. Now, if I restricted my domain, if I just said x can only be positive numbers, then it's a true thing to say. But in general, it's not true. Do we understand that? So you see a subtlety there. The domain is important. And of course, this would be true if we allowed ourselves to use a larger number system. Maybe some of you are familiar with the complex numbers. Does anybody have a question about this? I'll do a dance. Huh. So again, even though it's true for infinitely many numbers, it's also true, or excuse me, it's also false for infinitely many numbers. Therefore, in general, it's completely false. Does anybody want to say anything about this? Michelle, do you have any questions? I don't mean to pick on you, but you asked a question. I think someone else, Mackenzie, did you ask about this one too? I believe it was you. Not to pick on you guys, but that just shows you that you guys know I'm paying attention. And I care. I like your answer, Michelle. You understand better. See, you're very wise to realize you probably go home later and say, I don't know what happened. I want to swear real bad, but I can't. Where's everybody at today, by the way? It's the first day I had to really take attendance. Okay, let's do the last one. I like doing these together. Make sure you understand them. Oh my God, you're babysitting, Mackenzie. That's funny. Still getting paid by the peeps. We're going to do it. That's what I said, Michelle. Don't worry, Michelle. We're doing it. Why is my email popping up when I tell it to go away? What did it just tell me? Did I do something wrong? Oh, well, it doesn't matter. All right, so yeah, no, this is actually good that we're going to do these. I mean, the more examples we do, the better. You just got to really go home and say, I'm going to learn these creatures. So here's H. So now we're going to say for all x, there exists a y. So the same scenario as before, such that x plus y equals 10. All right, so we want to ask ourselves, is this true or false? And what I would encourage you to do is what we've been doing. Translate it for practice. Reads for all real x. There exists a y satisfying. When you add them together, you get 10. So we need to get, again, am I telling you something that's true? Or am I telling you something that's false? And it's actually bigger than that, because when I say this, this has to be true for any x. No matter what Fink does, the rest of his life, he can just randomly choose a number x. I have to be able to find a partner that I'm calling y. And the answer here is this is true. Why is this true? This is true because we can choose y equal to 10 minus x. Anytime Fink picks a number, I just take 10 minus x, and that's my y. And then when you add them up, you get 10. Very dry today. It's all about water. Once it hits your lips. Does anybody have a question about this? Does this make sense, Michelle? I mean, and there's nothing special about 10 here. I could have put any number there. That would have been true. And remember, we have these things called additive and multiplicative inverses. You know, it's funny enough, in almost every math major and computer science major on the planet has to take classes where they learn these symbols like this. But there's a big push, even by lots of mathematicians who think it's bad to even use this shorthand because they say it's harder to learn as opposed to using English. There's like a big divide. Now, doing certain things, like when you want to program computers and stuff, short and concise is better, right? But we're saying to learn these things, that you should write it out. So, I don't know. All right, does anybody else have any questions on homework 5 or homework 2? I think we've gone over almost all of them.
Just as a point of curiosity,
Yes.
personal curiosity, is this one we would say true due to like one of the, you know?
Yeah. So if you wanted to be really technical, like we're not saying this is a mathematical proof. See, there's sort of like a, so the question is, should we be, I think what you're getting at is, should we be more precise on exactly what we're using here? Like what logical reasoning? So it's kind of like circular, because we're saying that we want to learn this stuff so that we can teach you how to write a logical proof. Well, we're kind of giving you a fake proof, right? Like your intuition, exactly. So the question is like, okay, what axiom are we using here? Well, basically we're using a very simple thing. I call it the scale axiom. It's not really called that, but it's an axiom of arithmetic. Yeah. So one of the things we don't really talk about, they sort of do, maybe you did. I think that people who really see this are those who take like algebra in college, because then they kind of, at least that point, they beat down that there's these thing called natural numbers, and then we include 0 in their negatives, and we call them the integers, and then we have these real numbers. And then we talk about, we just all assume that the natural, what we call axioms, are true. Like if I take two numbers and add them together, I get another number. And so one of the axioms is if you have two things that are equal, you can add or subtract both sides and the statement is true. That's one of the axioms of arithmetic. You've used that axiom a bunch in your life anytime you've solved an equation. And I call it the scale axiom because basically what it's saying is, if you have you ever see an old triple beam scale, like You know, the old scales where you put something on one side, like a seesaw almost. And basically what you're saying is if it's already balanced, if the equation is true, you can add the same thing to both sides and it's still true. Or if you subtract the same thing from both sides, it's still true. So that's just an axiom of numbers. So it's a good point that you bring up, because mathematics, as I even said, is based off of this rigor idea that we start with definitions and axioms. That's what we start with. And every branch of math has its own sort of starting point. Some of you have seen this maybe in a geometry class in high school. When you do Euclidean geometry, we start with like 10 things. Well, really 11. You have the 5 axioms and you have the 5 postulates. And then there's this thing called the parallel postulate, which is like the 11th creature, I guess. And basically what you do is you just assume those to be true. 5 of them are completely true. It's like if you, just obvious things with arithmetic. If 2 things are equal and then something is equal to one of them, then all 3 things have to be equal, right? Like the transitive property maybe. Okay, so once we agree that these are true, then we just make definitions and try to logically deduce things from them. And that's kind of what we want to build up in here. We want you to get a sense of what is a good mathematical argument, what is a poor one. What is a good way to write an algorithm, what is a poor way to write an algorithm. There's very much crossover between those 2 things. Even programming is very much connected to this kind of stuff. And the textbook does a really good job of pointing all that out. I mean, we don't have enough time to go into all those things. That's why I said if you can get a hold of the book and read a lot of the stuff, or how they make a lot of good comparisons that show you where the math is specifically used in the computer science areas. But you'll see that in other classes. Okay, does that answer your question? Yeah, but it's like, I think I even mentioned it last week, and we had the one problem. I said, this is the multiplicative inverse, or this is the additive inverse. Those are things that you should be, we're just taking them for granted, that they're intuitive enough right now. Any number you pick for me, think, I can always find a number, we add them together, we get 0. You give me 7, I say add -7 to, right? That's called the additive inverse. Just like you give me any number, I can divide it by a number, and it's going to give me 1 all the time. So you divide by itself, or you could say you multiply by the reciprocal. Okay, so very good. So what's next then? How do we want to sort of handle this? Well, as I said, our goal is to be able to start to learn how to put together mathematical arguments. And what we use is we use these things which we call the rules of inference, is like the fancy word for this stuff. And there's a section in the book about this. And what I alluded to last week is I don't think it's the best learning idea to like study all that. I think it's better to just get right into doing arguments and referring to these things, because really the technicalities aren't what we care about as far as what is this rule called, or it's more about, is what we write down logical? If so, why? If not, why? Where are we making false conclusions? That kind of stuff. What rules are we using where? Are we allowed to use them there? How do we infer something from something else? And the best way, in my opinion, to do this is to just get right into it. Does that make any sense? Now, of course, some of this is going to look frightening for you guys, and that's okay. We're going to be loving it all the way to the bank, as they say. Okay, so we're ready to just jump into it. So let's get a different color. So proofs. So what we want to do is we want to say, okay, here's what we think about in mathematics. How are these things stated, or what are we interested in? What are the soul, sort of like the heart and soul of mathematics? And as we said, one of the most important sort of ideas in mathematics is this notion that we often want to assume as little as possible, And we want to know, what can we logically deduce from these assumptions and basic definitions? What can we say about these things that we create? You know, an example that it should be fresh in your minds is think calculus. We create these things, we define these things called functions. And then we define these new operations like differentiation and integration. And sometimes these things can be applied to a function, sometimes they can't. Some functions have derivatives, sometimes they don't. Some functions we can integrate, sometimes we can't. And so what we want to do is we want to say, okay, how do we figure out, how do we phrase these things in a way that's useful so that a theorem, and you've heard us use the word theorem before, even though we've never really defined it. What makes them useful? Okay, so let's say, first off, before we do that, does anybody have a question or a comment about sort of what I'm saying? So let's sort of give a sort of sketch of how things work. So typically, we start with definitions and axioms. So for those of you who don't know, so an axiom is a statement we assume to be true So for example, we're going to assume an axiom of real numbers would be if I take two real numbers and add them together, I get a real number. An axiom would be for every real number, there exists an additive inverse. There exists a multiplicative inverse. We all agree that this is true. And it doesn't take much to agree, like we just gave you the example. You pick 7, I pick -7. That's its additive inverse. You pick 7, I say 1/7 is its multiplicative inverse. So we all, those are things that are either through common sense or just the rules. We're saying these are true, whether you like it or not. Now, of course, you could define other systems where you use different axioms. And some of you will get to see that kind of stuff. We'll do a little bit of that in here. When I talked about modular arithmetic, the rules are different there. And so, from these, we logically deduce true statements. And so we often call these theorems. Sometimes we use lemmas. You may have heard this. And so, what does it mean then when we say logically deduce true statements? So that's kind of where we're at right now. This logical deduction is, so the logical steps that yield the theorems are called proofs. So instead of dealing with all this terminology, let's just go right into an example. And we're going to start with something that should be, I don't want to say it's obvious, but it should be sort of something that you can sort of get. Does anybody have a question? All right, so the first thing we're going to do is we're going to do what we call elementary number theory. So this is a good place to start. So a good place to start so this, when we say number theory, that's, I think it's very self-explanatory. This is a branch of math that we study properties of integers. So we need to make a definition. So let's recall. Integers are 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Those are the integers. Or sometimes it's a little more correct to perhaps write it like this. What we often do is we often abbreviate with this bold Z. And so how do we write a bold-faced Z on a blackboard? We can't, so we kind of write it like this. Now you're going to ask, why do we use Z when integer starts with I, and then go blame the German language because the word for integers in German starts with a Z. Does anybody have a question about this? So now we're going to make a definition of a word you've absolutely used a gazillion times in your life, especially if you went to school. Definition. Suppose n is an integer. We say it is even if there exists an integer k such that n is equal to 2 times k. We say n is odd if n equals 2k plus 1 for some integer k. So this is probably different than how you've defined even and odd when you were a kid. As a kid, you probably defined even as the multiples of 2. Or they said if you divide it by 0, the remainder is, excuse me, if you divide by 2, the remainder is 0. I don't know how you were taught what an even number was. But it turns out a very useful way of defining even and odd is that exactly what we did here. An even number is any multiple of 2. An odd number is any multiple of 2 plus 1. So what's nice about this definition is the first thing that you can say is every integer has to be even or odd. You can't be both. Now let's play a game. All right, someone pick an integer. Pick anything. Pick a number. 4. Well, 4 is equal to 2 times 2, right? So the corresponding k is 2. If I pick 26, 26 is the same as 2 times 13. So my k would be 13. Does anybody have a question about that? What about an odd number? What's 11? 11 is 2 times 5 plus 1. So 2 times k plus 1. Now, I mentioned this on the very first day of class. Turns out that number theory is one of the oldest branches of math, obviously, because counting numbers, 1, 2, 3. Right? But it also turns out to be extremely useful in modern times. As I alluded to, number theory leads into the math that's best used for things like encryption. And, so that means like making our digital world safe, so to speak. Okay, so here's our very first theorem. The very first thing we're going to study is, okay, what happens to numbers if I square them? So if I take an even number, is it square, even, or odd? If I take an even number, is its cube even or odd? All these kinds of things. These are very simple questions, and you might have some things in your head where you're like, okay, I get it. Let's take 2. If I square 2, I get 4. If I square 3, I get 9. If I square 4, I get 16. If I square 5, I get 25. So that pattern, you might start to think the square of an even number is even, and you might say the square of an odd number is odd. But how could we verify that logically? We can't just give you 3 examples and say it's got to be true for everybody. That's not how it works. Now, there's lots of patterns that work, and then one step, they stop. Does anybody have a question about this? All right, so here's one of our first sort of proofs that we're going to get to see. So we are going to prove that if n is even, then n squared is even. So we have to think about how we want to do this. How can, what tools, the logical tools that we had before, how do they help us here? So how can we do this? Well, so the first thing I would encourage you to do is first note what is this statement? This statement is a P implies Q, right? We're saying that P is the the statement n is even, and then Q is the statement n squared is even. So the couple things we want to point out, one of the most common things that things are stated in math, or I should say one of the most common ways we state something is we say if P, then Q. If you're differentiable, then you're continuous. If you're even, then your square is even. And so we want to think, I mean, we can go on and on and on. So we want to think of this as sort of like an agreement. We have a hypothesis, and we want to know is if we assume this hypothesis to be true, what is the conclusion? How do we verify it? So what we do is we do the following. So to prove P implies Q, what we do is we assume P is true, and then use logical reasoning to show Q is true. Now, we can't just do this for one integer or two or three. We have to do this for every one of them, right? Because that's what the statement said. It says, if you're an integer that happens to be even, this is what we can say about you. Now, we think it's a true statement because we did the first few examples in our head. We square 2, we square 4, we square 6. We get even numbers, so it seems odd, seems reasonable. And so then the next thing you want to do is you sort of want to sketch this argument. You want to say, okay, how do I do this? So let's just, for fun, here's our sketch of our proof. Or brainstorm our argument. Now, it's going to turn out with these baby ones that we're doing now, there's not much to say. But in general, proving a theorem or proving a conditional is not easy. Oftentimes, it requires lots of trial and error. It requires lots of different attempts at things before finally getting all the pieces of the puzzle together. So a common thing that hurts students when learning this is every textbook is usually not written that way. Every textbook is written theorem proof. And then it's almost like we don't see all the hard work that goes behind figuring out this proof. So notice I am not doing anything. I'm saying here's my sketch of my argument. So here's what I want to do. I want to assume that n is even. Okay, what does this mean then? Well, if n is even, what can I immediately deduce about n? Well, thus, n equals 2k for some integer k. So all I did I do anything difficult here? No. I said n is an even number, and then I wrote down the definition of what that means. That's all I did. Now, what I want to do is, remember, my ultimate goal was to study n squared. I want to know what structure n squared has. So, thus, n squared equals 2 times k quantity squared, which of course is equal to 4 times k squared. However, another way of writing 4k squared is recognizing that this can also be written 2 times, I'll use another letter, j, where j equals 2k squared. Even more particular is an integer. And so what we can conclude is we can conclude that n squared is even. By definition. I showed that n squared was 2 times an integer. Did I not? That's what I did. I showed that n squared is equal to 2 times j. That's 2 times an integer. That's what I needed to do. That was that is the definition. So I've just proven that n squared is even. Does anybody have a comment or a question?
Could you go back to the previous slide for a few seconds?
Sure. Yeah. Do you have a question about it?
Nah, I just wanted to write some
Cool.
stuff down. All right, you're good.
Sure. All right.
Yep.
Okay, so let's make an important comment. So what we did is we had P implies, and then we had a couple other intermediate steps, and then we had a couple intermediate steps, and then finally we showed that Q is true. So there's a name for this. This is called a direct proof. So we start with our hypothesis and we logically work our way to showing the conclusion is true. Does anybody have a comment, question? So right now you're going to say, what do you mean direct proof? Okay, but we're going to talk about different proofs. There's different ways of proving things. And you're going to say, what do you mean? Well, we spent some time talking about things that were logically equivalent. We made truth tables. So sometimes a direct proof can be difficult. And so instead we use another logically sound method. And so we're going to talk about different proofs as we proceed. So again, don't stress yourself right now over memorizing a direct proof, but just think about the argument and why we're giving this proof the adjective direct. Think about, we started with our hypothesis and we literally just sort of said, okay, what does this mean? Oh, it means this. And then what does that mean? Oh, it means that. And then it turns out the answer falls, not the answer, but the conclusion falls right out. And so here is a polished proof of that. Notice on the previous page, I said, let's sketch or brainstorm. This one was kind of, there wasn't much sketching or brainstorming because it was sort of just couple steps of logical deduction. There wasn't much involved in this. We wrote down the definition of what even meant. We used some basic properties of arithmetic and concluded that n squared had to be also even. So let's sort of write this in a polished sort of in a bow. So let's sort of formulate as a theorem. So theorem. If n is an even integer, then n squared is even. So that's our statement. And typically what we do is we write our polished proof underneath it. So here's our proof. So here we go. We're going to prove this directly. Our argument on the previous page worked, so let's just write it down. So let's assume that n is even. Therefore, there is an integer k satisfying let me not use satisfying. Let's use such that. There is an integer k such that n equals 2 times k. We will show n squared equals 2j, where j is an integer. So I'm being very descriptive here. I'm going to tell you what I'm going to do. See, the magic happened on the previous page. I already know what j is. I know. So I'm telling you that here's my integer that I'm going to write. I'm going to write n squared is 2 times some new integer. And I can't use k again. That wouldn't be silly. You know, we have to assume that k and j are different numbers. In fact, we already know how they're related. We sketched it on the previous page. All right, so let's go to the next page. So indeed, n squared equals 2k quantity squared, which is 4k squared, which is 2 times 2k squared, which is equal to 2j where j equals 2k squared. So by definition, n squared is even. You having fun yet? Does anybody have any questions about this? Comments? Now, of course, you might think this is overkill. Some of you might say this is an obvious statement. Why are you doing this? But what I'd like to show you is I'd like to show you all the lines of reasoning. It might seem silly to rewrite 4k squared as 2 times 2k squared, but that's the point. The point is we need to show that n squared is 2 times some integer. And so that's what I did. Now, of course, this goes under the assumption or the axiom, if you will, that 2 times an integer squared is also an integer. But, you know, that we agree that the integers are what we say closed. So what that means is take 2 integers and add them, subtract them, or multiply them, and they're always integers. You take 2 integers and multiply them, you get an integer. So if k is an integer, k squared is an integer. If k squared is an integer and you multiply by 2, it's also an integer. Okay? Does anybody have a comment or a question about this creature before we do another one? So the first thing I'd like you to understand about proofs is you should never write a polished proof right away, unless you've done it over and over again. The first important thing about proofs is you need brainstorming, you need sketching. There's lots of trial and error in proofs, and we usually don't reveal that as the finished product. Just like an artist doesn't really reveal all the hard work that it took to maybe make a painting or something like that, right? You only get to see the finished product. Mathematical proofs, especially in books, are often given that way. It's often the ideas and the sort of the ingenuity that went behind the proof is often not seen by you, the reader. It's kind of hidden away by the user, whoever constructed the proofs. So that's something you need to think about. Okay, let's do another one that's very elementary in this sense. Here's our next theorem. So let's see if we can get away with this one in a similar manner. So now let's assume if n is an odd integer, then n squared is odd. Oh, by the way, I should have mentioned this. It's typical in mathematics to if you're writing a proof, we typically like to let the reader know that it's done. And the old-fashioned way was to use this QED, which was, I believe, a Latin phrase that like translated that which was meant to be proven or something like that. But nowadays, you'll either see QED or you'll sometimes see, instead of someone writing this down to show the reader the proof's over, sometimes we'll just put like a block like this. And then that lets the reader know, or the viewer know, that the proof is over. Does that make sense? We'll see more of that as this time goes on. All right, so what I'd like to do before I give a formal proof is I want to divide this page into two pieces. Over here, I'm going to sketch my idea. Now, the reason I'm just reserving a little bit of space is that we would imagine that this argument is going to be very similar to the previous one, right? And it should just be some basic equation manipulation. So let's assume if I have n squared, excuse me, n is even, or excuse me, odd. N odd, what does that mean? Well, that means that n equals 2k plus 1. And then if n is equal to 2k plus 1, that means n squared is 2k plus 1 quantity squared. And then that means I can multiply this out and I get 4k squared plus 4k plus 1. And so remember, what is my goal? My goal is to make this look like 2 times something plus 1. So what I'm going to do is I'm going to recognize, okay, I got that 2. I know it's there. So if I pull the 2 out, I have my plus 1, so all that's left is to just write this like this. And then I can just give this creature a name, just like we did before. Let's call this creature right here. We used J before. How about we use M? So this particular theorem doesn't require much deep thought. It's just writing out what n squared is. And so now we can actually give a polished proof. So we assume n is odd. And we don't have to be so not worried, but so wordy. So that what does it mean to be odd? It means n equals 2k plus 1 for some integer k. And then, of course, all we need to do now is put this together. So we assumed n is odd. We wrote down what that meant. Now we want to show you that n squared is odd by showing it's 2 times something plus 1. So here we go. So to show n squared is odd, set m equal to 2k squared plus 2. And note, what is n squared? What is n squared? N squared is 2k plus 1 quantity squared, which is, if we multiply this out, is 2 times 2k squared plus 2k plus 1, which is 2m plus 1. And so that is a complete proof. Does anybody have a comment or a question? Anybody? Going once, going twice.
Would you have n squared equals 2k plus? Oh, never mind, never mind, never mind.
Sure?
Yep.
Any other questions? All right, let's do another theorem. And we'll end with this one. So if n and m are integers, well, let's say for the sake of it, so if n and m are odd integers, then n plus m is even. Take two odd integers, 7 and 5, add them together, you get 12. That's even, right? How we prove this stuff? So once again, it's useful to have a little bit of a sketch. So maybe I'll come over here and just write it down. So n and m being odd means n is, say, 2k plus 1, and then m would be, say, 2j plus 1. So n plus m would be 2k plus 1 plus 2j plus 1. And then we could write that as 2 times k plus j plus 2. Now, you might not see that right away, but I already see the end game. So maybe my experience is a little quicker than yours. So I factored out a 2 of k and j. And then what I could do is I could even break this down further. This is 2 times k plus j plus 1. So now that gives me everything I need. I have now written n plus m as 2 times something. That means it's even. So let's write our proof down. We'll just make it a little more clean than what we had over here. So here's another way that you might write this up. Let n equal 2 plus. So let's be more a little clear. So we're going to assume, we'll write out very clear. So assume n and m are odd. So that n equals 2k plus 1 and m equals 2j plus 1 for some integers, or for integers k and j. Okay, so we will show n plus m is even. So indeed, what is n plus m? N plus m, we saw on the left-hand side, is equal to 2k plus 1 plus 2 times j plus 1. And if you factor out the 2 from everybody, this is 2k plus j plus 1. And you might even say, instead of calling this a new letter, we can try a different strategy. We could say the following. So since k plus j plus 1 is also an integer, the proof is complete. Does anybody have something they want to share or say about this? Comments? All right, well, we're past time, so I will say thank you, and please reach out if you have any questions. I will talk to you guys on, some of you, I guess, tomorrow. The rest of you, I will see on Wednesday. I'm going to stop recording now. Thanks, guys. Take care. I appreciate it. Josh.